Now, in a calorimeter, since we're looking at a temperature change, we can be using MCAT. So we'll look at the increase in temperature. Now, this time, or decrease, but often these are going to be increases, we're going to be looking at the change in temperature. That's the key. All right, and this is going to give you the amount of energy in calories, or more likely joules. We want to relate this to the calorie, though, for you, just so you get some perspective of how it compares to food. So we're going to use our little MCAT formula. But at this point, we're going to use Q of our process, our reaction, or combustion, whatever it is going to be equal and opposite signs to Q of our surroundings. So that's going to be equal minus the mass times the heat capacity times delta T. Whoops. For our surroundings. So you really want to think carefully about whether these are endothermic or exothermic reactions. Let's take a look at the first one. Example 1413. We have a sample of sucrose, and it's burned in a calorimeter. Now, let's think about this. Logically, a combustion reaction gives off heat, so delta H of this combustion would be equal to a negative value. We expect it to be exothermic. And in an exothermic, the temperature of the surroundings does increase. So that temperature is measured for your surroundings. Now, Q for my combustion then is going to be equal in magnitude but opposite in sign of Q of the water, and that's going to be equal to the 240 grams of water times the heat capacity of water times the temperature change. And remember, you have to do final minus initial. So it's 27.55 minus 22.53. Final minus initial. And if we do that, we do end up with a negative 5040 joules as the delta H of combustion for the sucrose. Now, I want to get a little bit of perspective on that, so let's take a look at what that converts to in terms of food calories. So if we have 5,040 joules, and 1 calorie is going to equal 4.184 joules. And a food calorie, 1 food calorie, we usually use a capital C for that, as opposed to a lowercase, is 1,000 little calories, energy calories. If we did this, that amount of sugar is only equal to 1.20 calories in terms of food. Okay? That gives you a tiny bit. That really wasn't very much. 240 grams, excuse me, 0.303 grams of sugar is a very, very tiny amount of sugar. Now, it's common to have to calculate the kilojoules per mole of this. And the reason is we don't just record blank kilojoules. We have to have it on some sort of comparison scale. So in order to do that, we need to convert those grams of sugar, 0.303 grams of sugar to moles of sugar. Mass to moles, use molar mass. We know that. And that molar mass is 342.22 grams. And that's going to give us 8.85 times 10 to the minus 4th moles of sugar. Now to get kilojoules per mole, that means I have minus 5,040 joules for every 8.85 times 10 to the minus fourth moles. And I want to get kilojoules to joules to kilojoules. And if we did that, we're going to get 5.7 times 10 to the third kilojoules for every mole of sugar that we would combust. Now the question asks us, and actually that's going to be a negative, the question asks us, would heat be listed as a reactant or a product? That's part 4. Now, since it was exothermic, delta H ended up being a negative value, meaning that if I graphed that on a potential energy curve, I'd have my reactants at a higher energy than my products. So reactants would be higher than products on a potential energy curve. That means that heat would go on the product side, meaning heat is released as a product. Let's take a look at another one of these. This time we have octane. So I have 1 gram of octane, a much larger calorimeter, which we're neglecting the actual structural components of the calorimeter and focusing just on the water. So Q of the combustion is going to be opposite Q of the water. Opposite sign, equal magnitude. So that's 1,200 grams of water. The heat capacity of water is 4.184. You should be very familiar with MCAT by now. 33.20 final minus initial. If you don't do final minus initial on MCAT, you're likely to get the wrong answer. So Q of combustion is minus 41170 joules. Now, that was joules for 1 gram that was combusted. That would be one way of looking at it. Now, as we go on to the next one, and by the way, you know you can always pause this if you need to write something down or you want to try the next step on your own. But the next step is going to be taking those joules per kilojoules or joules per gram and getting them into kilojoules per mole. Now, you can do this in 2 separate steps like I did last time, or we can set it up as one step. The process released that many joules for 1 gram. Now, you can convert that mass to moles separately and then divide, or you can put it all in the same dimensional analysis. I want to eliminate grams. I put them opposite. They were in the denominator, so I put them in the numerator. Octane has a molar mass of 104.16. And then I want to get rid of joules and go to kilojoules. 1 kilojoule, 1 times 10 to the third. So here I did it all as one dimensional analysis. You could certainly have done it in 2 steps like we did in the previous problem. And if we have all of our algebra right, we have 4,290 to the correct, nope, 4 sig figs, I can do 88. Minus 4,288 kilojoules for every mole of octane that is combusted. So hopefully you're getting the hang of this. There's one more of the combustion ones, and I'd really like you to give that a shot on your own and wait until you've tried it once before you watch the next video.